Alright, so in this video I'm going to solve some trig inequalities. And the problems are posed so that we could just type these into our calculator, our graphing calculators, and get answers using like the intersection feature. But I want to go through an explanation trying to tie a bunch of things together. So let's make connections back to graphs of trig functions, let's make connections back to the unit circle, and let's see how much understanding we can get out of these without using our graphing calculators. At the very least, hopefully this will tie some different concepts together, and then when you do use your graphing calculator, the answers that you're getting might make a little bit more sense. So this problem says, the temperature in a certain city is modeled by the function below, where x is the day and f of x is the temperature in degrees Fahrenheit. For how many days to the nearest whole number each year is the temperature predicted to be greater than or equal to 70? And here's the equation we're working with. So f of x equals 68 plus 6 times the sine of 2 pi over 365 times x minus 90. So let's start real basic. A lot of people are very visual learners, especially with something like trig, so let's get an idea of what this graph might look like. I know that sine starts in the middle, and then it goes up, and then down, and then back like that, and that would be one full period of the sine graph. Normally that would be 2 pi, but I'm pretty sure the period of this equation is not going to be 2 pi. Actually, I remember that the equation is that the period equals 2 pi over b. And in this problem, the b value is that 2 pi over 365. So if I'm going to divide by this fraction, I guess I could rethink of that as multiplying by the reciprocal. So instead of dividing by 2 pi over 365, I'll multiply by 365 over 2 pi. And that's great because this 2 pi is like over 1, and so I can cancel this 2 pi and this 2 pi. So we're left with 365. And maybe that was obvious, because this problem is talking about temperature over the course of a year. Like x, or the input, is days, and the output is temperature. And it makes sense that over the course of the year, there's going to be one time where there's like peak temperatures and one time where there's like lowest temperatures. So yeah, the period is 365. And normally a sine graph would be centered around this midline of 0, but this one's been moved up. This equation has been shifted up 68. So the midline is 68. And the amplitude is 6, so that tells me it's going to get 6 units higher and 6 units lower from that. So 68 plus 6 is 74, and 68 minus 6 is 62. So we took care of the amplitude and the vertical shift. We took care of the difference in the period compared to a normal sine function. And then this x minus 90 is just going to shift the whole graph right 90 days. And this is 365 over here. 90 is about a quarter of that. So like here's the halfway point, here's the quarter way point. So I guess this sine function is going to start somewhere over here. And it might look something like that. So back to the problem, we've got a pretty decent visual now, and we're looking for where the temperature is predicted to be greater than or equal to 70 degrees. And 70 degrees is probably right about here on the y-axis. So if I continue that over as a horizontal line, we're looking for where it crosses, where these two things intersect. So I see two intersection points. That makes sense. They're looking for how many days it's above 70 degrees. Well, this stretch here is the number of days where the temperature is above 70 degrees. So if we get this x value and this x value, we could just subtract them and find the distance between them. And so that's our goal. We're going to have to take this equation, we're going to have to solve it for where it equals 70, because the output, remember, was 70 degrees. So I'll rewrite the equation so we have some room to solve. But then the question is, how are we going to get two answers out of this? Because this is just one equation, there's one variable here, x, that we have to solve for. So to make sense of this, let's actually connect it back to the unit circle. Whenever you're solving a trig equation, let's just keep it really simple. Let's say maybe sine of theta equals 1/2. We're looking for this angle where the sine value equals 1/2, and that would be the angle pi over 6. And we're looking for this angle that also has the same sine value of 1/2. It's the same height. This angle would be 5 pi over 6, for instance. Now that's not actually relevant in this problem, but that's the kind of idea. We're looking for two different angles. So let's get rid of all that, and we can use this unit circle to draw actual relevant values from this problem. So we've got this big long equation, and it does look pretty scary. I mean, there's a big fraction here, we've got sine, we've got a lot of stuff going on. But let's just take it one step at a time. I need to solve this for x, which means I need to get it alone, and that means I need to get rid of all this stuff on the outside. So let's first start by subtracting 68. So then 2 equals 6 times the sine. And then still working our way in from the outside, now we'll have to divide both sides by 6. And 2 divided by 6 is 1/3. And now is where the actual trig comes in, because we have to get rid of sine. It's not like I'm going to divide by sine, that's not a thing. We're going to do the inverse sine of both sides. So we end up with the inverse sine of 1/3. And then on the other side, inverse sine and sine just cancel each other out basically. So I'm left with the 2 pi over 365 times x minus 90. And I changed colors here because this is kind of the first big step in this problem. So far, subtracting 68 and dividing by 6 has been fairly simple. And now we'll have to use our calculator for inverse sine of 1/3. And that's because the value 1/3 isn't something I'm familiar with on the unit circle. It's not like we have some special triangle where the sine value equals 1/3. I know it's going to be about here, because here's where sine equals 1 at the top, so a height of 1/3 seems like it's about there. But I know there's the second location that has the same height of 1/3. But these aren't special triangles. It's not like a 30, 60, 90 or a 45, 45, 90. So using our calculator to type this in, making sure we're in radian mode, especially because there's this pi coming up in the problem, we get about 0.34. But here's where we got to back up a little bit, because our calculator told us 0.34, but it only gave us that one angle. This is 0.34 radians. It only gave us that one angle because that's the only one in the arc sine range. Remember, inverse sine will only give you answers between positive pi over 2 and negative pi over 2, and that's what it did. But we know there's this other angle that has the same sine value of 1/3. It's not in the arc sine range, but we still need to know about it for this problem. Well, look at the symmetry here. If this angle is 0.34, like the size of that angle, the size of this angle is also 0.34. So if I start at this angle, which is really close, and that angle would be pi, I'll just have to take pi and then subtract 0.34, because now we're rotating in the negative direction, or like backwards. So pi minus 0.34 is about 2.8. So there's our other equation. I'll just write both of them here, just so it's kind of organized. And now I just have these two equations that I need to solve for x. Again, let's just be patient here. Let's back up and make some connections. Because what we're trying to solve for in this problem is the number of days where the temperature was above 70 degrees. So we want to find these x values, these two x values. Well, so far we found two theta values. These are angles on the unit circle. When I solve for x, and by the way, this top equation is going to tell me x1, because that's the first angle, that's going to be the lower x value, and this is going to tell me x2, because that's the second angle, that's going to be the higher day value. Those will tell me the two x values, and then I can just subtract them, and there's my answer. So I rewrote the equations here just to give us a little bit more room to work, and now we just have to solve for x twice. And we're going to have to do the same exact steps in both of these equations. Here I want to get rid of the 2 pi over 365, so I'll divide by 2 pi over 365. Remember, that's the same thing as multiplying by 365 over 2 pi, which is still a little bit cramped over there. But that's a little bit easier to type in your calculator though. So we cancel that out. We get 19.75 roughly on the left side. And then we'll have to add 90, don't forget that last step. So our final answer would be 109.75 equals x1. That's the first day. Now that doesn't mean 109 days is the answer to the full problem, like 109 days the temperature is above 70 degrees. That is just the first day of the year where the temperature reaches 70, and now it's going to get higher than that for a little bit and then come down, and we need to find that second day where it hits 70 degrees. So again, we divide both sides by 2 pi over 365, which again is the same thing as multiplying by the reciprocal, 365 over 2 pi. That cancels, and we get 162.66 roughly equals x2 minus 90. And then again, don't forget to add the 90 over. All right, so we found the 2 days of the year where the temperature crosses over 70 degrees, and now we just have to find the number of days between them. So subtract them. So the answer is 143 days. Now, if you're using your graphing calculator to do this problem like they suggested, you're just going to type in this equation into y1, and then in the other equation, or y2, you would type in 70, and then you're going to see where they intersect. And again, your calculator is going to tell you these two x values should be the same two x values that we found, but then you'd still need to subtract those two x values to find your final answer. Now, if that problem was making sense for you, maybe this is enough of the video and you don't need to watch anymore. I'm going to work through another problem as an example. There's just a couple key differences. This one is a less than or equal to problem, and it's a cosine equation. But for the most part, it's going to be the same type of work, and I'm going to do basically the same explanation, just maybe hearing it a second time with some different numbers might help it to really sink in. So this problem says the number of hours of sunlight in a certain city is modeled by the function below, where x is the day and f of x is the hours of sunlight. For how many days to the nearest whole number each year is the hours of sunlight predicted to be less than or equal to 5 hours? So just like in the last problem, we're going to have to solve this for where it equals 5. And we could jump right into solving, but I think it's a good idea to get a visual going first. So for this equation, it's a cosine equation now, and I know that cosine normally starts at the top and then dips down and then comes back up. The period would normally be 2 pi, but again, this problem has a b value of 2 pi over 365. It's the same b value as before, so I'm not going to show that work, but we found that the period was 365, 1 full year. This equation was also moved right 90, just like the last one, so about a quarter of the way through the year is where the actual starting point would be. And then it'll dip down and then come back up like this. Also, the midline for a cosine graph would normally be at 0, but this has been moved up by 6. So the midline is at 6, and the amplitude is 4, so it's going to get 4 units higher and lower than this. So the top of the graph will be up at 10, and the bottom of the graph will be down at 2. So I guess at its peak, this graph gives us 10 hours of sunlight per day, and then at its valley or lowest point, we're looking at 2 hours of sunlight per day. It's pretty low. But again, I think that visual is really helpful because now we're looking for where this graph is less than or equal to 5 hours. And 6 is the midline, so 5 is right below that. So we're looking right about here. Where does this graph cross over 5? Again, if you want to jump right to your graphing calculator, you type in this into y1, and you type 5 into y2, and then you find these two intersection points. This first point looks like, it's less than 365. The second point is more than 365. That's kind of interesting. But then if we find that space between them, that will tell me how many days the hours of sunlight is less than 5. We're going to do it algebraically because that'll help us practice our solving skills, and we'll get a chance to look at the unit circle again, and inverse trig functions actually. Just like in the last problem, we're going to start with some pretty basic steps. So we're subtracting 6 from both sides. 5 minus 6 is negative 1. And then we have to divide both sides by 4. And now that I've gotten the trig function by itself, and it equals negative 1/4, we can start to think about the unit circle. So I remember that cosine is related to like an x value on the unit circle. So I want the x value to be negative 1/4. Well, negative is this way, and 1/4 is pretty small. This is negative 1 over here. So negative 1/4 would be like that. So it's going to be this angle up top and some angle down here. But these aren't angles that I know anything about. Like 1/4, negative 1/4 is not something relevant to any special triangles. These aren't 30, 60, 90, or 45, 45, 90 triangles. Just like in the last problem, we're going to have to use our calculators and do inverse cosine. In the last problem, I didn't mention this until after we found these values, but I just want to point out that we're going to be using inverse cosine. And the inverse cosine range is the top 2 quadrants. So I'm expecting that our calculator is only going to give us this one answer. So I take the inverse cosine on both sides. That leaves me with inverse cosine of negative 1/4 on the left, and then there's no cosine function on the right anymore. And I'm getting 1.82 from my calculator. But this is where it's a good idea to pause and again make a connection back to the unit circle. The calculator gave us this one angle, 1.82. And that makes sense. Like pi is over here, it's about 3.14. Pi over 2 is up here, which is about 1.5-ish. So yeah, this angle being 1.82 is a little bit past pi over 2. Yeah, that makes sense. But we know there's another angle down here that's relevant. That's going to give us the second day that we're looking for. And the only real value I know here is that this is 1.82, that angle. Like the size of this rotation is 1.82. And we can use some symmetry. So like if this is 1.82 on top, the symmetry shows me that this would also be 1.82 on the bottom. It's just this is rotating in the negative direction. So now we're going to have to start here at 0, or maybe we should call that 2 pi, and then we'll subtract 1.82 from that. And that'll give you about 4.46. Now the question is, why do I know to call this 2 pi instead of 0? And it's just because if I started at 0 and subtracted 1.82, that would give me a negative number, which is probably going to change to a negative number of days. That doesn't really make sense. If we look back at our picture, I don't want to be traveling backwards to find some number of days in the past. I would rather travel forwards and find the higher angle or the higher number of days. So we have 2 equations to solve. One of them in purple here, 1.82 equals blah, 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 and the other one is going to be 4.46 equals blah, blah, blah. So I rewrote the equations a little bit clearer, gave us some more room to work. Again, we're going to divide by 2 pi over 365. You're probably getting bored with this by now because I've done it a couple times. And remember, that's the same thing as multiplying by the reciprocal. This goes away, and I got 105.7 out of that, and that equals x minus 90, and then we just have to add 90. So we have 195.7. That is our first day that we're interested in. And then if I just speed through the same work for the second equation, I'm assuming if you're watching this video, you know how to like add and subtract and multiply and divide and all that. We get 349.1. So there's our second day that we're interested in. If we just subtract those two numbers, that'll tell us how many days the number of hours of sunlight was less than 5. The other thing I wanted to point out, and this is why I really think it's important to get a visual before you dive into a problem, is right away we recognize that the second answer was going to be about, something more than 365 days. I didn't know what to do with that information, but it just seemed kind of interesting. And now that I finished the problem, I can kind of check my answer. The second day is 349. That's not actually more than 365, but that's just because my picture is not drawn to scale very well. The important thing is just that we recognize that the second answer is going to be pretty big. It's at least close to 365. And the other one, 195, that's close to half of 365. It's a little bit more. So it makes sense that this first answer shows up roughly here. And again, this is just a rough sketch, but it gives me an idea of if my answers make sense or not. So we end the problem by saying that's 153 days total.